Whenever you're ready.
Hi, I'm Andrea Belrath, and I'm here to show you a way to slow down and make sure students really understand new concepts that you show them, new math skills in computation. There are 3 stages to computation, whether the students are learning how to count or add for the first time, or whether they're learning how to multiply 2-term expressions in their algebra class. Any new computation skill, they should start by understanding what it is that you're asking them to do. So for this, you could say that we're learning to add 4 plus 5. You could have manipulatives. You could have little teddygrams and have 4 teddygrams and another 5 teddygrams and have them count out how many teddygrams that is altogether. Or you could have drawings if they were learning to multiply 4 times 5. They could have 4 circles with 5 tally marks in each of those circles. But the goal here is to make them really understand what this new skill is. A part of this is to have real-world examples. You should break out the story problems as soon as possible so that they understand what this new skill actually is, how it's useful, why they should care about it, and what it means. Once they have, for multiplication, drawn their circles and their tally marks so often that they are sick and tired of it, they might come up with a strategy to make this faster. So strategies involve flexibility. The students don't have to, every single time that they're multiplying, draw circles and put tally marks in it. They could learn to, say, count by 5s. Or they could learn that when you don't know your 7s times tables, if the problem was 7 times 5, that they wouldn't have to count by 7s. They could count by 5s instead, that 7 times 5 is the same thing as 5 times 7. All of those little tricks that help students do things more quickly are at this stage. The important part of this is that students should be the ones who come up with this. You should not give your students a big, long list of strategies. These are things that, as you have been showing them, laboriously drawing things out, they should say, hey, wouldn't it be faster if we tried it this way? That way, it makes the learning come from them. They know that it makes sense because they were the ones who thought of it. And even if it wasn't the individual student who thought of it, if it was their classmate that came up with it, they know that it made sense instead of just being something that came from the textbook. These stages should not be rushed. You should spend as long as you need on them. They should take at least a day each. Hopefully, this whole process would take at least a week. Eventually, you'll get to the algorithm. That's knowing the one right way of doing it. If you were adding double-digit numbers, that's when you learn how to carry. If you were multiplying, that's when you know to put this number on top of that number. There's one set way that everybody eventually learns, but you don't want to have them learn that first, because if they learn this too fast and they haven't had time to look at the strategies, they haven't developed much number sense, if they haven't had enough time to spend on the understanding, they might not even understand what this skill that you've taught them how to do is, how it applies to anything. So eventually, you'll want to teach them the one right way of doing this and have them memorize things. But these 2 steps are important parts of the learning process. Let's go ahead and apply this approach to a problem that 5th grade students might face. 3 1/4 multiplied by 2 1/2. So to start with, the stage 1 approach. This means to make sure that they really understand the problem by making sure they can see when it would be useful in the real world. So for example, maybe there's a board that is 3 1/4 feet one way and 2 1/2 feet the other way. and they're trying to figure out how many square feet the board is. You can draw some pictures. What if you drew the board out and you knew that the board was 2.5 feet this way? So 2 feet would be that much, 1/2 foot would be there, and that it was 3.25 feet the other way. So if this is as big as an entire foot is, then that would be as big as 1/2 foot is, and 1/4 foot would be about that big. Well, this is 1 foot on this side and 1 foot on that side. So there's 1 square foot. They could go ahead and figure out how many of the whole square feet they have. And they'll eventually get to that being 6 of them. And then they'll have to figure out, but how big are these pieces? Well, if this is as big as an entire square foot was, then this would be 1/2 of a square foot, as with this one. There, as with this one. And over here, if this is the size of an entire square foot, this is 1/4 of a square foot. I'm just going to put 1/4. There's not quite enough room for my label. And that would be another 1/4. And then they get to that crazy corner piece. But if you know that this is an entire foot and that this would divide it into 4ths and that this would divide it in 1/2, now you've got 1, 2, 3, 4, 5, 6, 7, 8 pieces, and 1 of those 1/8 is part of your board. And then you'd work with the students to figure out, what is this all together? Well, you've got 6 of these entire feet, and 1/2 and 1/2 makes 7, and 1/2 and 1/4 is going to get you to 8, and then you add on this extra 1/8. So this would get you to 8 and 1/8 square feet. Now that took a long time to do. There are faster ways, and your students can come up with them. Up here, we have 3.25 times 2.5, but the students might, instead of thinking of this as an area model, they might see it as an operator. They might say 2.5 copies of 3.25. So 2 copies of 3.25 would be, let's see, how about start with 2 copies of 3. So 2 copies of 3, well, that's 6. And then you could take 2 copies of 1/4, and that would get you 1/2. And then you still got a 1/2 copy left of 3.25. Well, 1/2 a copy of 3, that's 1.5. And then 1/2 a copy of a 1/4, that's going to be 1/2 as big. So that'll be 1/8. And then the students might say to themselves, well, if I've got 1.5 and an extra 1/2, Let's make that be 2, and maybe add our whole numbers together and get that to be 8. And then 8 and an eighth is 8 and an eighth. And then going back to the original problem, that it was square feet. This way didn't take as long. The students should be the ones who realize this. And if not all the students realize this, if you can find 1 or 2 students who go about it a faster way, you can have them explain to the rest of the class what it was that they did to make this faster. Now this looks very different than what we did at stage 1. Stage 2 doesn't have to look too terribly different. Another way of doing this that would still be faster is to just have an open array. If instead they had drawn 3 and a fourth and 2 and a half, it could be they would just split this array into 4 parts that don't have anything to do with the relative sizes of the pieces, but they could still multiply this easily. At this point, they might know that 2 times 3 is 6, and that 3 times a half is 1 1/2, and that 2 times a fourth would get you a half. And then they would put these parts together. This is actually very similar to this. You can see that they got the 6, and they got the 1 1/2, and they got the half, and they got the eighth. But it still looks awfully similar to what they would have done back in stage 1. This is another way of them figuring out a faster approach to this problem on their own and developing insights along the way. Now, eventually, students will get to stage 3. Remember that stage 3 is the tried and true algorithmic approach, how grown-ups always remember this problem going. So if you have 3 and a fourth times 2 and a half, the first step would of course be to take this 4 and multiply it by the 3, which gets you 12, and then you add 1. So you would end up with 13 fourths times, well, 2 times 2 gets you 4, plus 1 more gets you 5 halves. And then you have to multiply. So 13 times 5. Well, let's go over into a corner and let's write that 13 and put the 5 underneath it and multiply this out so you have the 5 times the 3 gets you the 5. And you carry the 1, and then you have the 5 times the 1 gets you 5 plus 1 gets you 6. And then you go back over here and you write in that that's 65 over, and then 4 times 2 gets you your 8. But this is an improper fraction instead of a mixed number. So let's go back over here and let's do a little bit of, well, if this is double digit over a single digit, I suppose we really should do long division at this point. So let's go ahead and put our 65 on the inside and our 8 on the outside. And how many times does 8 go into 6? Well, none at all. And then how many times does 8 go into 65? Well, I guess that's going to be an 8 times 8 gets you 64 minus equals 1. So that means remainder 1. And then you come back over here and you say that that means that this equals 8 and 1 more out of 8. And that took an awfully long time. This problem could be solved 3 different ways, but there's no saying that this way that we just did was any faster than the strategy. Lots of times the stage 3 approach is the one that we stick with because it's the one that always works, but it's not always the very fastest way of getting this done. And sometimes stage 2 approaches can help you with other math later on. So this process of multiplying fractions should be pretty tried and true by the time the students hit 7th and 8th grade. But the process of having learned this through stage 1, stage 2, and stage 3 will help the students in their math in this grade too. For example, you might realize that 3 and a fourth, technically speaking, That's 3 plus a fourth times 2 plus a half. And the method of solving this could be awfully similar to something else multiplied a 2-term by a 2-term, like say x plus 2 times x plus 3. They could use the exact same method that they had used over here by having 3 and a fourth multiplied by 2 and a half. They could work out the same way that x plus 2 times x plus 3 would be x times x, or a square x, and x times 3, and 2 times x, and 2 times 3. Now, you might say, but they have a way of solving this. They could use FOIL. Now, FOIL is a stage 3 approach. It's memorizing that they would look at the first, and then the outsides, and then the insides, and then the last terms, and multiply these one at a time. And yes, this does work, but it's not as conceptual of an approach, which means that it makes it tough for them to apply it to other situations. For example, if you were to, instead of having a 2-term by 2-term, you tried to multiply something with 3 terms, suddenly FOIL doesn't work. But this deeper understanding they developed all the way back in 5th grade will help with this strategy they came up with. You can just go ahead and add an extra term and multiply out and find your answer. So all of these stages, going through the understanding and then the strategies before finally arriving at the algorithm, takes a lot longer than simply teaching the students a procedure. Why do we care? Why do we want to go to something that takes so much extra time from our busy schedules? Well, one thing is that going through these other stages lets this understanding link to future learning, like we showed with the learning of 2-term multiplication from your fraction multiplication all the way back in 5th grade. Another reason that we want to do this is that by having gone through stage 1 and stage 2, when you arrive at stage 3, when you're using the algorithms, there's a good chance that they're the ones who will have come up with the algorithms. For example, the multiplying of reciprocal, when you're dividing fractions, that multiplication of reciprocal is easy enough that it might be that they were the ones who came up with this in the first place, and then they'll know why it should and when it should not be applied to the math that they're showing. Another reason to keep this process slow enough to make sure they understand it every step of the way is that rushing straight to the stage 3 algorithm masks misunderstandings. For example, the problem 50 plus 3. Well, everybody knows when you have a double-digit number, what you ought to do is you ought to line up the 50 and put the 3 underneath it, right? And then you just add, and you end up with, let's see, so the 5 plus the 3 gets you an 8, and 0 with nothing gets you 0. So then the answer is 80, right? Students who have been rushed to stage 3 don't necessarily realize why they're doing any of these steps. So they have no way of knowing that the 3 ought to be in the 1's place because they've never stopped to break a number apart into, if it was 24, to break it into 20 plus 4, as opposed to just rushing straight to this and saying, let's put these numbers underneath each other. Another way they might mistake it is, well, 50 plus 3, so that's 53, isn't it? If they happen to know in their heads that this is the 10s and that there's some 1s after it, and then 50 and 3, so 50 and 3, right? So there's lots of ways that students can have misunderstandings and not have these things corrected for years and years. You can run into 5th or even 6th graders who don't understand any of these computational steps because they never learned them. They never learned why they work, only how to do them. I know that these steps, going through first understanding and then strategies and then algorithms, will take an awfully long time, but by the time you've finished, they'll truly understand why they're doing these things, and it will help them with their future studies.